In our previous lessons, we discussed how functions can work together to break down a large problem in small bits and pieces and solve it from the ground up. But this wouldn't be much of use if the functions can't communicate. This is where parameters and arguments come in. They allow functions to pass data to each other to be able to modify the same copy of data, thereby solving the problem. You'll recall that in C, there are two types of function arguments, namely actual arguments and formal arguments. We're going to visit this just now. To fully understand what we're trying to get at here, let's take a step back and look at function arguments in more detail. As we just mentioned, function arguments basically take two forms. That is, actual and formal arguments. This has to do with how the arguments are passed. The variables declared in the function prototype or definition are known as formal arguments. These are demonstrated here. In this code snippet, x and y are the parameters. Although formal parameters are typically variables, it doesn't really mean that they're always variable parameters. And it's not strictly set that they are variables. You can use numbers, expressions, or even function calls as actual parameters. The other type of argument is called actual parameters. Actual parameters are not in the form of declarations, as are their formal counterparts. Actual parameters are the ones implemented in the call to the function at any time during the code. Just now, we were looking at the methods that are used to pass arguments to functions. But why do we need to do that in the first place? Well, a function is just a bunch of instructions. These instructions aren't really useful if they don't have data to work with. This data can be passed to function using the methods that we outlined above. Or the variables can be declared in the function itself and used within the function. A function can receive arguments in two ways. The first way in which this can be done is receiving the argument as a value, which means that a copy of whatever the function is going to be working on is passed on to the function. The other way in which it is done is by passing the address of the variable that the function is going to be working on. This means that the function would directly access whatever is contained in that address and also directly modify it. This is in contrast to passing by value, where the computer only works on its copy of the variable and doesn't affect the actual variable that is stored in the address. This has varying results on the final state of the variable after the function has completed execution. Whenever you're writing a C program, or any program for that matter, whenever your function requires data from somewhere else, you typically provide this data in the form of arguments. This is a fairly straightforward process most of the time. But have you ever stopped to think, what would happen if you don't know the number of arguments that your function will take at runtime? Variadic functions come to the rescue here and allow you to accept a variable number of arguments at runtime. In all the programs that we've written so far, once we write the code and compile it, it is pretty much set in stone, and we can only edit it by terminating the running program and going back to the source code to modify it, adding whatever it is that we want to add. Now, this is a problem, mainly because in the real world, we typically don't really know how much data the program will encounter at runtime. Also, you won't always be around to alter the source code when the user wants to use the program. Luckily, C has a built-in mechanism that will allow us to send a variable number of arguments to a function. Let's take a look at this more closely. As with quite a lot of things in computing and programming, we don't know the number of things that we're working with. These are only known at runtime, and this poses a problem for the computer. This is because we normally assign values to variables, and the number of variables that we need during programming and these are set in stone during compilation. It is normally not a problem when you set the upper limit if you have an idea of how many elements you'll be working with. When you define an ordinary function and add a specific number of arguments to it, it forces you to supply that specific number of arguments whenever you call that function. This works very well for functions that have a fixed number of arguments, such as our quadratic equation solver from one of our demos. Now, in that example, if we had to create a function, we know it will always take the 3 arguments that represents the values of a, b, and c. Pretty simple, right? Contrary to what you may think, there are actually functions that perform meaningful routines and expect a variable number of arguments. Some of these functions can handle any number of values by operating on all of them as a block. In our last lesson, we learned about the malloc function. This function brings about so many possibilities, but also brings about problems. You can allocate memory dynamically during runtime, but how will you access all the additional memory slots that are created? Variadic functions solve this problem by allowing you to supply the function with a variable number of arguments. This means that, for example, you can have one function that creates any number of array elements, and the function that works on that array becomes a variadic function. In this way, you can be sure that if free memory is not allocated, the malloc function has a corresponding argument to it. Problem solved. A much easier and more relatable example is that of the printf function. You've seen in all the lessons that we've done so far that the printf function can handle just about any amount of information that you throw at it. This is an example of variable arguments. Anything that you put into the printf function in between the parentheses is an argument. It gets passed to the printf function that then works whatever wizardry it does so that the information is displayed on the screen. You can have anything between just one character to a long line of text and output from variables without running into any errors. Let's take, for example, this code snippet that has variable numbers of arguments in it. In this code snippet, the printf function takes 3 arguments on the first instance. In the second instance, the printer function takes 2 arguments. Both of them are perfectly correct and won't produce any compilation or runtime error. The scanf function also works in pretty much the same way. Remember when we read a number of different inputs from the keyboard and stored them in different variables? It was exactly the same concept that we just applied here. Variable arguments offer you greater flexibility with regards to what you can do with your function. When dealing with variadic functions, at least one named formal parameter must appear before the ellipsis parameter. To get a clear picture of what is going on here, let's go back to the function that we just talked about, the printf function. If you dig deep into the standard library header file, you'll come across this code. That probably all looks pretty cryptic, but the good news is that it's only just there so that the rest of the explanation makes sense. Let's now take a closer look at the data types and macros. Surprise, surprise! The printf function is not the one that does all the magic that we've seen on screen. The printf function just passes everything onto the vfprintf function, and all the magic and spells happen there. That is not exactly our point of interest though, so we're not going to dig much deeper than that. In both functions, which refers to the printf function and the vfprint functions, 3 macros and 1 special data type are used to implement the variadic functions, namely va_start, va_arg, va_end, and va_list. Let's now look at the skeletal version of the function that handles these parameters. First up, we have typedef va_list. This is a list of variable arguments. A char variable which will be initialized by the address of the first variable argument. Argument. It's an opaque variable that holds information about which argument we're going to get next with VARG. The computer just keeps calling the function VARG repeatedly. The VA list variable is like a monitor that tracks where we're at in progressing with the list. In spite of that, we still need to initialize that variable to a value that makes sense. Now that's where VA start comes into the picture. When the computer calls VA start, VA count, it is initializing the variable VA to point to the variable argument that is immediately after count. Interesting. It's becoming even more clear why we have at least one named variable in our argument list. With that pointer pointing to the initial parameter, the computer can easily get all the following argument values by calling VARG repeatedly. When you want to do the same, you have to pass your VA list variable together with a type of argument you're about to copy. Next, we have the void VA start, which takes the parameters VA list, AP, and PN. This is a macro which takes a VA list variable AP and the last name parameter PN as its input and initializes AP by adding the size of PN to its address. After calling VA start, the pointer AP will point to the address of the first unnamed parameter. After this initialization process, we then have a macro retrieving the value of the next unnamed parameter. It takes the VA list variable AP and the type of the next unnamed parameter T as input and returns the value of the next unnamed parameter. The assumption here is that an actual argument is always passed. This means that if the VARG function is invoked and there are no more arguments, it results in undefined behavior. This probably looks familiar to you. And yes, it's not just some hullabaloo from a dream that you had last night. It's the standard argument header file. We've covered this already in previous lessons, but it is of particular interest today because it enables us to use the functionality battery we have been discussing earlier. Its contents are the key drivers of variadic functions, as we're going to see shortly. Quite a lot of what we have just discussed in the previous section is actually part of the contents of this header file. Interesting, isn't it? Well, let's take a closer look. The primary focus of this lesson was to show us how to write programs that accept an indefinite number of arguments. This is exactly what the standard argument header file does. We took a peek at it in one of our previous lessons, but we kind of just skimmed the top and didn't really get much into it. Typically, the size of the unnamed argument list is generally an unknown value. Because of this, the calling conventions that are used by most compilers don't allow you to determine the size of the unnamed argument block pointed at by VA list inside the receiving function. There is also no reliable universal function and foolproof way to pass these unnamed arguments into another variadic function. Even if your device has some genius way of determining the size of the argument list indirectly, like parsing the format string of fprintf, it'll just hurt the portability of your code because when you pass the dynamically determined number of arguments into the inner variadic call, the number and size of arguments passed into that call will still need to be known at compile time. You could, to some extent, get away with this restriction by using variadic macros instead of variadic functions. In addition to that, most standard libraries provide an alternative way to access the unnamed argument list. For example, an initialized VA list variable instead of the unnamed argument list. An example of this is vfprintf, which is an alternative to the fprintf function. It expects a VA list instead of the actual unnamed argument list. A user-defined variadic function can, following this logic, initialize a VA list variable using VA start, then proceed to pass it on to the relevant standard library function, which has the indirect effect of passing the unnamed argument list by reference instead of passing it by value. The library function then has direct access to the list. Because there is no reliable way to pass unnamed argument lists by value in C, providing variadic API functions without also providing equivalent functions accepting VA list instead is considered bad programming practice. Some other versions of C have built-in C extensions that allow the compiler to check for the proper use of format strings and sentinels. If the compiler does not make use of these extensions, as is usually the case, the compiler can't check whether the unnamed arguments passed are the type the function expects, or convert them to the required type. It is then left up to you, the programmer, to make sure that everything is correct, because if anything doesn't match, it results in undefined behavior. If, for example, the expected type is int asterisk, then a null pointer should be passed as int asterisk null. Writing just null would result in an argument of type either int or void asterisk. Both forms are incorrect and will result in undefined behavior. You should also take into consideration the typecasting conversion that we discussed in previous lessons. Type promotions and demotions will also result in undefined behavior. Since we already know how values are promoted and demoted, the function that is receiving the arguments must be programmed in such a way that it expects the new types. Did you know that the famous Hello World program, which is usually the first program people write in C, exposes some of the most dangerous features of the language? If there are insufficient arguments for the format, the behavior is undefined. Now comes the time that most of us have been waiting for. Remember in Module 1, we promised that we're going to create a small project in which we're going to build code as we went along. At this point in our course, we have sufficient knowledge and information to develop a small but functional app that actually does some work. As we learned from Module 1, a computer program starts its life as a problem statement. When you, as a computer scientist, read this problem statement, your head is already bubbling with potential solutions to the problem. But we also learned in Module 1 that you don't just jump into writing code. If you do so, chances are you end up with a hot mess that either works as intended, but is incredibly slow and clunky, or you just simply end up with a hot mess of spaghetti code that doesn't work at all. We also learned that to avoid this, you have to plan the solution using a series of steps. Let's just jog our memories a bit. Step 1 is to build a solution. When you encounter a problem, the first thing to do is to think of the possible ways in which you can solve the problem. It can help to write down the solutions and look at them to find which one is probably the best one to follow. After writing down these solutions, you then pick out the one you think is the best one. From then, you flesh out the probable solution in all the ways that you can think of right off the bat. This includes any functions that you might think are necessary for the solution to function. Before you even get to functions, it would be helpful to think of the strategy that the program will follow. This makes it easier for the next step, which is writing pseudocode. Of course, this is not set in stone, as you can start with a flowchart instead of the pseudocode. My personal preference is starting with pseudocode, as you can easily alter it without making too many changes to the entire program. So for now, we will go with that. Step 2 is write the pseudocode. Pseudocode, as you remember from Module 1, is fake code. You also remember there's no compiler on Earth that can compile and run pseudocode. It doesn't conform to the strict syntax and semantics of programming languages. This gives you a great deal of flexibility when strategizing how the program will work. We need to flesh out the pseudocode as extensively as possible, and this gives us a rough idea of what the flowchart will look like. And of course, We can always go back to the pseudocode and alter it as needed at any time in the development process. After we finish with the pseudocode, we will be ready to draw our flowchart. At this point, our program will be in such a state that you can follow the logic and see how the solution will work. Like the pseudocode, the flowchart needs to be as detailed as possible. This makes it a lot easier to change the flowchart and the pseudocode to actual code. It is important here to try and stick to what you wrote in your pseudocode as to keep things consistent. When you're done with that, the next step will be to write the actual code. Okay, so the next step is to write the actual code. Like we mentioned before, it'll make your life a whole lot easier if you stick to what you wrote in your pseudocode. This is not always possible, and that is a reason why it is called pseudocode anyway. It's just there to guide you as you go along with your program and to help you keep a visualization of your completed solution in mind. Later on in the module, we're going to learn about the various techniques that I use for testing, which is what you will need to do straight after finishing your code. In our next lesson, we will look at the software development process, and this will give us a very good idea of how we should handle the development process. In case you're one of those who are interested in sneak previews, our small project will be on a system that accepts student details from the user, calculates average marks and totals according to the school's specifications, then displays the marks on demand to the user. Our program will also employ a command line menu from which the user can pick which functionality of the program they want to use. As we go along, we'll add functionality that we will have learned about and integrate it into the existing code. By the time we get to our 8th lesson, we will have a fully functioning program that runs in command line and is able to fulfill all the requirements that are specified by the user. Interesting times ahead. Now, this lesson may feel like you're diving into the deep end. So instead of spending more time talking and looking at theoretical concepts, it is better if we spend most of our time in a demo, looking at how it actually works. Today's demo is on a program that accepts a variable number of arguments and displaying the list after processing the data. Pay special attention to the syntax that we're going to be using in the demo, as this is what you will need whenever you want to use variable arguments. In today's demo, we're going to be looking at variable arguments. So if you remember from earlier in the lesson, we discussed that a function or a program can have a variable number of arguments. And this is useful when you want to conserve memory by just allocating memory for the objects that you want to be working with. This actually turns out to be quite useful in a number of situations. Imagine you're at a party and you want to create a profile for everyone who comes to the party. But the problem is, you don't know how many people will be at the party. So it's really difficult to create a program that caters for everyone. You might create a program that can store information for 5,000 people. Then the party turns out to have 10,000, and your program will run out of capacity to deal with all that data. And this is where variable arguments come in and allow you to create variables on the fly. To demonstrate how this works, we have this simple program that will accept a variable amount of marks and add them together to calculate the average mark for the student. Now we'll just run through the code before we execute. It's just to see how it works. As usual, we have up top our header files and the standard input-output header file. As you know already, it allows us to use input and output functions in the program. And the standard argument header file is what we're most interested in today, which allows us to use variable arguments. Straight after that, we have this function that has the most interesting feature of this program. This is where all the variable arguments magic is being carried out. Notice that this function, named addition, takes the argument a, and we have the ellipsis here, which we mentioned that is put in there for the machine to know that you're using variable arguments, and that variable is used for generating the variable list. We're going to see where this function comes into play in a bit. So straight after that, we go into the main function where we straight away declare an array, the variable num and I and count, which will initialize to 0. And we also declare a double, which we will name sum, and initialize it to 0. So straight after that, we're going to ask the user how many subjects they want to work with. And that is going to be stored in num. Then straight after that, we're going to ask the user to enter the requested number of marks, which are going to be stored into a variable argument list. And this is where this function comes into play. So whatever is in the array gets passed to this function and added to the variable argument list. And then our function goes through this for loop, adding all the numbers that are available in this variable argument list until it gets to the very end. And for the most straightforward part, we divide the sum by count, and count referring to the number of iterations that we went through, so that we get our average. And straight away, we go to print our average. Right, now that we've gone through the program, go ahead and hit F11 or F11 to compile and execute the program. So let's say we want to enter 3 subjects. Then press enter. So let's say we got a 98. Sorry, that's 98. And 82 and a 70. And there you have it. We have our average. So let's say we execute the program again. And this time we enter 5 subjects. We have 99 and 80 and 80, 80 and 97. There you have your average. If we look closely at our program, it's not really saving memory as much as we want to, because if you look at the main function, we have this array that is being declared with 50 elements. Now, it doesn't use the full potential of this variable argument list. We can expand by changing this to something that uses maybe a malloc or some other method like that. So I will leave you to look at the program and see just how much memory you can save by tweaking it around a bit and making sure you remove this pre-declaration of an error and make it dynamic. That's all for this demo.